Okay, welcome back. We're moving on to section 19.2, and this is called the Fourier transform. The first step actually is to recognize that using Euler's formula, we actually have an equivalent representation of the Fourier series. Every cosine n pi x over L can be written as e to the 2 pi n x over L, and there's an I there, plus e to the I, negative I, 2 pi n x over L, all divided by 2. And we have a similar property with sine, where you can write sine 2 pi n x over L as e to the I 2 pi n x over L minus e to the minus I 2 pi n x over L divided by 2I. Okay, so recognizing these properties of cosine and sine, they let us rewrite the Fourier series, maybe from our last section, right? We have both Fourier series as cosines and sines. We're going to now rewrite them as exponentials. And in doing so, we actually recover a Fourier series which looks like this. Okay, and it's the same as before, where this Cn. This is why I started out the whole Fourier series section with what I said. The Cn necessarily has to be the inner product of f with each of the complex exponentials here, because of that same property that I started out at the beginning of the last lecture. These coefficients will always be the inner product so long as we have an orthonormal basis. Which in this setting, right, recall that that's 1 divided by L, integral 0 to L, f against the conjugate of e. So there's a minus I there, 2 pi n x over L dx. So that's going to be the Fourier series if you decide to write it with complex exponentials instead of cosines and sines. We call the c sub k's, which I just stopped writing, but of course that's this, 0 to L, f of x, e to the minus I, 2 pi n, I guess there's a k there, right? 2 pi k x over L dx. We call this as a function of k, right? Because there's a k right there, a k right there, and actually there's a k right here. So as a function of k, we call that the Fourier transform. So the transform is thinking about, okay, what are these coefficients, but now interpreted as themselves a function of k. That's what the Fourier transform is. So if I scroll down, we can take the Fourier transform of the square wave, and I'll jump back over to the whiteboard to calculate this out. Maybe we can calculate the Fourier transform of the same square wave we were dealing with the last time. This is the function that's 0 to the left of L over 2, and it's the function that's 1 to the right of L over 2. And the Fourier transform is just what I had written down on the previous page. It's the integral from 0 to L of f against the complex exponentials with a negative I, 2 pi k x divided by L dx. Okay, so let's actually calculate this integral out. The 1 over L can stay along for the ride. Just like in the last case, the only time the integral sees anything are for values of x greater than L over 2. So we start at L over 2 and end at L. We just have e to the minus I 2 pi k over L. I'm going to put all that in parentheses, x dx, because I'm going to use the really fancy formula that the integral of e to the ax dx is e to the ax divided by a. And so I'm going to use that with a being negative I 2 pi k over L. And that's going to give me, I guess, L divided by L negative I 2 pi k. And then I'll end up with everything I started with, e to the minus I 2 pi k over L x. Evaluated at the boundaries L over 2 and L. If I simplify what's out front a little bit, that's going to give me I divided by 2 pi k. And then I evaluate the exponential on the boundaries, and that gives me e to the minus I 2 pi k minus e to the minus I pi k. And if I simplify these, I can simplify these using Euler's formula for e to the minus I pi is negative 1. So I end up with actually 1 inside the parentheses here. This is 1 to the k, because that's negative 1 squared to the k, minus negative 1 to the k, which 1 to the k is just constantly 1. So what I actually have here is I 1 minus negative 1 to the k over 2 pi k. And that is the Fourier transform f hat of k, where my original function was that square wave. So let's jump back to the book and see if the book agrees with me. To go through calculations. Yeah, everything looks the same. All you have to do is distribute that negative 1 to the k, and then everything would look the way that I wrote it. So I guess my notation is a little bit better. But that's actually all I have. There's just a few more things there that it talks about where there's actually a version of the Fourier transform where you take your integral over plus and minus infinity instead of just 0 to L. There's a way to take the limit as L goes to infinity. Okay, we can also talk about the Fourier transform as an operator, and what this means is that we can use a letter, it's the calligraphic F. Often I'll use a script F if I'm writing it myself. So you can use a letter to represent kind of the transformation of starting with a function of x and ending with a function of k. Right? This is an operation which has been performed on the function, and we can represent that operation using a capital F. Now, what this actually looks like, because we know how to construct f hat, this just looks like the inner product. This is the same as the inner product of f of x with e to the I 2 pi k x over L, which happens to be the integral 0 to L f of x against e to the minus I 2 pi k x over L dx. Okay, so you can represent this operator in many ways. You can represent it directly as the operator, you can represent it as the f hat, you can represent it as an inner product, or you can represent it as an integral. They're all equivalent. But the nice thing is that we have an inverse operator, f inverse, which reconstructs your regular function by the integral, or actually the sum, right? So it reconstructs the function using the series, the Fourier series, 2 pi k x over L, and we're starting at minus infinity and we're ending at positive infinity. So we have a way of representing, maybe pushing ourselves into this space that we call the Fourier space a lot of the times, and pulling ourselves out of this space. Now, something that's useful is that this transform is a unitary linear operator. So what we mean by that is that actually linear, you'll recall, just means that it's able to distribute and commute with scalars. So that's why I have an f hat and a g hat there. I don't have to worry about the plus sign or the alpha. And unitary, we'll recall, is this property of inner products. It says that the inner product of f and g is equal to the inner product of f hat and g hat. And the inner product of f hat and g hat, since they're really in this setting a true infinite vector, looks like f hat of k, g hat of k star. K goes from minus infinity to infinity, whereas on the left-hand side, this just looks like 1 divided by L, integral 0 to L, f against g star dx. Right, so the fact that these two quantities are equal is no tiny feat, but it's a very useful feat because sometimes we like to calculate infinite sums, or sometimes we like to calculate integrals because one can be easier than the other. And that's a really useful technique in a lot of physics, is to convert yourself into a transform space and compute the inner product there because the numbers work out better, or vice versa. And so that's just something to keep in mind, is that we're also unitary, which means our inner products are the same no matter where we decide to take them. Anyway, that's all I have. I'll see you in class. Bye.